There is a place inside the Earth that no human instrument has ever directly measured. No probe has descended to it. No drill has come close. It sits nearly 4,000 miles beneath the surface, spinning in darkness, generating forces that reach into space, and it may be changing in ways we have only recently begun to suspect. The core of the planet is as remote as any distant moon, yet it determines much of what makes this world habitable. And scientists now believe it may be doing something it has not done in human memory, something gradual, invisible, and patient. A shift measured not in years, but in the silent accumulation of time itself. The Earth's core exists in a state of extremity that resists imagination. It is made primarily of iron and nickel, compressed under pressures more than 3 million times greater than the atmosphere at sea level, heated to temperatures that rival the surface of the Sun. The outer core, which begins roughly 1,800 miles beneath your feet, is liquid metal in constant motion, churning in slow currents that have persisted since the planet's formation. Deeper still, at the very center, lies the inner core, a solid sphere of crystallized iron approximately the size of the Moon, suspended in that molten ocean, rotating independently of the rest of the planet. This is not metaphor. The inner core spins at its own rate, decoupled from the mantle and crust above it, separated by a boundary where liquid meets solid in pressures and temperatures no laboratory has fully replicated. The forces that govern its behavior are fundamental, ancient, and largely invisible to human observation. We know the core exists not because we have seen it, but because we have listened to the planet. Seismic waves from earthquakes travel through the Earth's interior, bending and reflecting at boundaries between different materials, arriving at distant seismometers with information encoded in their timing and amplitude. Scientists have spent more than a century interpreting these echoes, constructing models of the deep interior from indirect signals. The core does not reveal itself willingly. It speaks only through vibrations that pass through thousands of miles of rock, and even then, the message is incomplete. What we call knowledge of the core is really a form of sophisticated inference built layer by layer from waves that have crossed the planet and returned changed. The picture is remarkably detailed, but it remains a picture, a representation built from shadows and echoes, not direct contact. The inner core's independent rotation was first proposed in the 1990s, a hypothesis that seemed almost impossible to confirm. How do you measure the spin of something you cannot see, buried under half the diameter of the Earth? Researchers found a way by studying pairs of nearly identical earthquakes that occurred years apart in the same location. The seismic waves from these earthquakes traveled through the inner core and emerged on the opposite side of the planet, where seismometers recorded their arrival. By comparing the waveforms, looking for tiny shifts in timing and pattern, scientists detected changes that could only be explained if the inner core had rotated slightly between the two earthquakes. The evidence was subtle, encoded in differences of a few tenths of a second, but it was there. The inner core was not locked in place. It was moving. For years, the consensus held that the inner core rotated slightly faster than the rest of the planet, a phenomenon called superrotation. The difference was small, perhaps a fraction of a degree per year, but over decades it added up. This rotation was thought to be driven by the magnetic field generated in the outer core, which exerts forces on the solid iron below. The inner core, in this view, was like a rotor suspended in a magnetic engine, pulled forward by invisible lines of force. The idea fit elegantly with models of Earth's geodynamo, the process by which the planet generates its magnetic field. But science built on inference is always provisional, always subject to revision when new data arrive. In recent years, analysis of seismic data has suggested something different. Multiple research groups have reported that the superrotation of the inner core may have slowed, paused, or even reversed. The evidence comes from examining decades of earthquake records, tracking the subtle changes in how seismic waves pass through the inner core over time. Some studies suggest the inner core stopped its faster rotation around 2009, entering a period of near synchronization with the mantle. Others propose it may now be rotating slightly slower than the surface, a state that could represent part of a longer cycle. The data are complex, and interpretations vary, but the possibility has become impossible to ignore. The inner core, it seems, does not spin at a constant rate. It responds to forces we are only beginning to understand, forces that operate on timescales far removed from human perception. This is not a sudden event. It is not a shift that announces itself with earthquakes or magnetic storms. If the inner core has indeed changed its rotation, the transition unfolded gradually over years or decades, detectable only through the patient accumulation of seismic observations. The planet does not experience such changes as disruptions. The forces involved are immense, but they act slowly, redistributing momentum and energy across distances measured in thousands of miles. The magnetic field continues to exist. The outer core continues to flow. The surface remains stable. What has changed, if anything, is a detail in the deep choreography of planetary motion, a detail with implications we have not yet fully grasped. The difficulty lies in the nature of the evidence itself. Seismic waves do not provide a continuous view of the core's rotation. They offer snapshots separated by years, filtered through layers of rock with their own complexities. Different earthquake pairs sample different paths through the inner core, and the structure of the core is not uniform. There are variations in density, anisotropy in how seismic waves travel depending on direction, and uncertainties in precisely where those waves have passed. Two research teams analyzing the same data can reach different conclusions depending on their models and assumptions. This is not a failure of science. It is the reality of studying something so distant and inaccessible that every measurement is an act of interpretation. The core does not offer certainty, it offers clues. The forces that govern the inner core's rotation are not simple. They emerge from the interaction between different regions of the planet, each with its own properties and motions, coupled through gravity, magnetism, and the friction of viscous flow. The outer core, that vast ocean of liquid metal, generates Earth's magnetic field through a process called the geodynamo. As the molten iron moves in complex patterns driven by heat escaping from the core and by the planet's rotation, it creates electrical currents, and those currents produce magnetic fields. The fields in turn influence the motion of the conducting fluid, creating a self-sustaining system that has operated for billions of years. This magnetic field does not remain confined to the core. It extends outward through the mantle, through the crust and into space, forming the magnetosphere that shields the surface from solar wind. But it also reaches inward, into the solid inner core, exerting torques that can accelerate or decelerate its rotation. The inner core responds to these magnetic forces, but it is also gravitationally coupled to the mantle above. The mantle is not a uniform shell. It has density variations, regions where rock is slightly heavier or lighter, warmer or cooler, and these heterogeneities create a gravitational landscape that the inner core moves within. If the inner core is not perfectly spherical, and evidence suggests it is not, then its interaction with the mantle's gravity can exert additional torques, influencing how it spins. There is also the possibility of friction at the boundary between the solid inner core and the liquid outer core, though the nature of that friction is not well understood. These forces do not act in isolation. They combine, compete, and shift over time, creating a system of remarkable complexity buried in a place no instrument can reach. The rotation of the inner core, then, is not a fixed property, but an outcome, a balance point that can shift as the forces change. If the magnetic field generated by the outer core strengthens or weakens in certain regions, the torques acting on the inner core change. If the pattern of convection in the outer core shifts, redistributing where heat and motion are concentrated, the forces shift as well. The inner core does not control these changes. It responds to them, adjusting its rotation over timescales that may span decades or centuries. What we observe as a slowing or reversal of superrotation may be part of a longer oscillation, a cycle in which the inner core periodically speeds up and slows down relative to the surface. Or it may represent a more persistent change, a new equilibrium that will last for millennia. The data available cover only a few decades of a process that operates on geological time, and definitive answers may not arrive for generations. This is the nature of planetary science at its most fundamental. The processes that shape a world often unfold at rates that exceed human lifespans, sometimes by orders of magnitude. We arrive in the middle of a story that began billions of years ago and will continue long after any record of our observations has vanished. The tools we have, seismology, geomagnetism, computer modeling, allow us to glimpse fragments of that story, to reconstruct how the planet behaves when no one is watching, but they cannot provide the full narrative. We are observers at a timescale mismatch, trying to understand a symphony by hearing only a few notes. Consider the magnetic field itself. It is not constant. The field has reversed its polarity hundreds of times in Earth's history, with the magnetic north and south poles swapping positions. These reversals are recorded in ancient rocks, where cooling lava preserved the orientation of the magnetic field at the moment it solidified. The intervals between reversals vary wildly, sometimes a few 100,000 years, sometimes tens of millions. The field also wanders, with the magnetic poles drifting slowly across the surface even when no reversal is occurring. And the field's intensity changes, growing stronger or weaker over centuries. All of this variability originates in the core, in the shifting patterns of flow in the outer core that generate the field. If the inner core's rotation is coupled to the magnetic field, then changes in one may reflect changes in the other, but the relationship is not straightforward. The geodynamo is a system with many moving parts, and isolating cause from effect requires models that are still being refined. What we know with greater confidence is that the core's behavior does not threaten the surface. There is no scenario in which a change in the inner core's rotation causes earthquakes, floods, or atmospheric collapse. The energies involved are vast, but they are distributed across the entire planet and expressed over long periods. If the inner core has indeed entered a phase of slower rotation, the transition happened without anyone on the surface noticing. The magnetic field continues to protect the planet. The day length remains essentially constant. The continents drift at the same imperceptible pace they have maintained for millions of years. The core is changing perhaps, but the planet as a whole absorbs that change without disruption, integrating it into the slow dance of geological process that has always defined this world. Still, there is something compelling about the idea that deep within the Earth, beneath all the complexity of surface life and weather and human activity, something fundamental may be shifting. Not quickly, not violently, but with the patience of a system governed by planetary-scale forces. The core does not care about human timescales. It operates according to the physics of rotation, magnetism, and heat flow, indifferent to observation, indifferent to consequence. It simply is, and it changes when the balance of forces dictates that it must, and it will continue in whatever new state it assumes for as long as those forces allow. The inner core is not simply a ball of iron. It is a crystal, or rather an immense assembly of iron crystals grown under conditions that render the distinction between solid and liquid almost meaningless. At the pressures found at Earth's center, more than 360 gigapascals, a number that corresponds to millions of atmospheres, iron takes on a structure called hexagonal close packed, a lattice arrangement where atoms are stacked in layers, each atom surrounded by 12 neighbors in the most efficient configuration possible. This is not the iron of the surface world, malleable and prone to rust. This is iron compressed until its electrons are forced into new orbital configurations, iron that exists in a state of matter with no terrestrial equivalent. And yet it is solid, or solid enough. It has rigidity. It can sustain shear waves, the seismic vibrations that only travel through materials capable of resisting deformation. The inner core, despite its temperature of roughly 5,000 degrees Celsius, does not melt, because the pressure is so overwhelming that the atoms cannot move freely. They are locked into place by the sheer weight of the planet, pressing inward from all directions. This crystalline structure is not uniform. Studies of seismic waves passing through the inner core reveal that it is anisotropic, meaning that waves travel at different speeds depending on their direction. Waves moving parallel to Earth's rotation axis pass through faster than waves traveling along the equatorial plane. This suggests that the iron crystals are aligned, oriented preferentially in certain directions like the grain in wood. How this alignment arose is still debated. It may have formed as the inner core grew, with crystals precipitating out of the liquid outer core and settling in response to the planet's rotation and magnetic field. Or it may reflect processes occurring within the solid inner core itself, where slow convection or deformation gradually reorganizes the crystal lattice over millions of years. Either way, the inner core is not a homogeneous sphere. It has structure, texture, and history written into its atomic arrangement, a record of formation and change that we perceive only as variations in seismic wave travel times. The inner core is also growing. It has been growing since it first formed, roughly 1 billion years ago, as the planet slowly cools and heat escapes from the interior. The outer core is still hot enough to remain liquid, but at the boundary between the outer and inner core, the temperature and pressure conditions are such that iron crystallizes out of the molten metal and adds to the solid sphere below. This process is not uniform across the boundary. Evidence suggests that more freezing occurs on one side of the inner core than the other, possibly due to variations in heat flow from the deeper interior or to the influence of the mantle above. On the side where more crystallization happens, the inner core grows faster, and on the opposite side, the solid iron may even melt slightly, returning to the liquid outer core. Over time, this asymmetric growth causes the inner core to shift, not in position, but in its internal structure, as material slowly flows from the faster-growing side to the slower-growing side, redistributing mass and maintaining balance. The process occurs at a rate measured in millimeters per year, invisible and patient, governed by the logic of thermodynamics and planetary heat loss. The growth of the inner core has implications that reach beyond the core itself. As iron crystallizes and freezes onto the inner core, lighter elements dissolved in the liquid outer core are left behind, released into the surrounding fluid. These lighter elements, probably sulfur, oxygen, silicon, or some combination, are buoyant compared to the denser iron. They rise, creating convective currents that help drive the motion of the outer core and sustain the geodynamo. In this sense, the inner core is not a passive object. Its growth actively powers the magnetic field, providing the energy needed to keep the outer core in motion, despite the friction and resistance that would otherwise cause it to slow. The magnetic field, in turn, influences the rotation of the inner core, creating a feedback loop that connects the planet's deepest interior to the space environment far above the surface. The system is self-regulating, complex and ancient, a machine built by accretion and heat, operating without design or intention. The age of the inner core remains uncertain. 1 billion years is an estimate, but it could be younger or older, depending on assumptions about the planet's initial temperature and the rate of heat loss over time. What is clear is that for most of Earth's history, there was no inner core at all. The planet was hotter, the entire core was liquid, and the geodynamo operated in a different regime. At some point, the center cooled enough for the first solid iron to appear, a seed crystal forming in the heart of the molten sphere. From that moment, the inner core began its slow accumulation, growing outward atom by atom, layer by layer, as the planet radiated its primordial heat into space. It is still growing now, and it will continue to grow as long as the core remains hot enough to generate convection in the outer core. Billions of years from now, if the planet survives long enough, the entire core may solidify, the geodynamo may cease, and the magnetic field may vanish. But that is a distant future, so far removed from the present that contemplating it feels less like prediction and more like myth. For now, the inner core exists in a state of slow transformation, spinning within its ocean of liquid metal, responding to forces that shift on timescales incomprehensible to those who live on the surface. Its rotation may be changing, its growth may be uneven, its structure may be more complex than models suggest, but these changes do not announce themselves. They accumulate in silence, detectable only through the careful analysis of seismic echoes and the construction of models that remain forever provisional, forever subject to revision as new data emerge from the depths. The boundary between the outer and inner core is a surface unlike any other in the solar system. It is not a place you could stand, not a shore or interface in any conventional sense. It is a transition that occurs at a specific pressure and temperature, where liquid iron becomes solid iron, where the chaotic motion of the outer core meets the locked structure of the inner core's crystal lattice. The boundary is not perfectly smooth. Seismic studies suggest it may have topography, regions where the solid surface rises or dips by a few kilometers, creating relief comparable to mountain ranges on Earth's surface. But these features, if they exist, are not carved by erosion or tectonics. They form through the interplay of crystallization and melting, through variations in temperature and composition, through processes that operate in a regime where intuition drawn from surface geology offers little guidance. Imagine, if the comparison helps, what it might be like to approach that boundary from above, descending through the outer core. There is no light. There has not been light for thousands of miles. The darkness is absolute, unbroken by any source of illumination, because photons cannot exist freely in molten iron under such pressure. There is no sound as you would recognize it, though the fluid is in constant motion, currents flowing in patterns too vast and slow to perceive as distinct events. The temperature is beyond the melting point of any material familiar from the surface, yet the pressure is so intense that the concept of melting loses its usual meaning. You are surrounded by iron in a state that is both flowing and constrained, moving in eddies that may persist for centuries, but leave no trace except in the magnetic fields they generate. As you descend further, the pressure continues to rise. The liquid iron becomes denser, its atoms packed more tightly though it remains fluid. The temperature may be increasing slightly, or it may be decreasing. Models disagree, and the uncertainty reflects how little direct information we have about conditions at this depth. Then, at a certain point, the liquid begins to change. Crystals form, small at first, suspended in the fluid and then larger, connecting into a lattice that extends in all directions. You have reached the boundary. Below this point, the iron is solid, locked into its hexagonal, close-packed structure, and above it the iron flows freely. The transition is not instantaneous. There may be a zone of partial melting, a region where solid and liquid coexist, where crystals grow and dissolve depending on local conditions. The boundary is not a line but a gradient, and its exact position may shift over time as the planet cools and the inner core continues to grow. No instrument has ever sampled this boundary directly. No probe has descended into the outer core, and none will for the foreseeable future. The challenges are not merely technical, but fundamental. At depths of even a few hundred miles, the pressure and temperature are sufficient to destroy any known material. The drills and sensors and cables that work on the surface would vaporize or compress into uselessness long before reaching the core. The deepest hole ever drilled, the Kola superdeep borehole in Russia, reached only about 7.5 miles into the crust, less than 0.2% of the distance to the core. Even if engineering could somehow overcome the material limitations, the energy required to drill through thousands of miles of solid rock and then molten metal would be astronomical, far beyond any conceivable budget or infrastructure. The core remains inaccessible, not because we lack the will to explore it, but because the physics of the planet itself renders direct exploration impossible. What we know, then, comes from inference, from the patient assembly of indirect measurements into models that approximate reality without ever touching it. Seismology provides the foundation. Every earthquake generates waves that propagate through the Earth, and those waves behave differently depending on the materials they pass through. By analyzing the travel times and amplitudes of seismic waves recorded at stations around the world, scientists can construct tomographic images of the interior, mapping variations in density and structure. It is similar in principle to medical imaging, where X-rays or sound waves reveal the hidden structure of the body, but the scale is vastly larger and the resolution far coarser. The models show the core, its layers, its boundaries, but they are reconstructions, interpretations of data that have been filtered through thousands of miles of rock and processed through algorithms that make assumptions about how waves travel. The magnetic field offers another line of evidence. Measurements of Earth's magnetic field at the surface, combined with observations of how that field has changed over time, allow scientists to infer properties of the outer core where the field is generated. Variations in the field's strength and orientation reflect changes in the flow patterns of the molten iron. and those flow patterns in turn depend on the temperature, composition, and dynamics of the core. Computer models simulate the geodynamo, solving the equations of fluid dynamics and electromagnetism in a rotating sphere, attempting to reproduce the observed magnetic field and predict how it might evolve. These simulations are among the most computationally intensive in all of science, requiring supercomputers to calculate the interactions of turbulent, electrically conducting fluid over millions of simulated years. The models have become increasingly sophisticated, but they remain approximations, limited by resolution and by gaps in our understanding of the core's properties. Laboratory experiments add another dimension. Scientists can subject samples of iron and other materials to pressures and temperatures that approach those of the core, using diamond anvil cells or shockwave experiments, and measure how the materials behave. These experiments reveal properties like melting points, electrical conductivity, and seismic wave velocities, which are then incorporated into models of the core. But the conditions at the boundary between the outer and inner core are so extreme that even the most advanced experiments struggle to replicate them fully, and extrapolating from laboratory measurements to planetary scales introduces additional uncertainty. All of this effort, the seismology, the magnetism, the modeling, the experiments, converges on a picture of the core that is detailed enough to make predictions, but incomplete enough that surprises remain possible. The suggestion that the inner core's rotation has changed is precisely the kind of surprise that emerges from this ongoing process of refinement, a detail that was not anticipated, but that becomes visible when the resolution of observations improves and new methods of analysis are applied to old data. The changes occurring in the inner core, if they are indeed occurring, do not manifest in ways that most people would notice. The Earth continues to rotate once every 24 hours, the sun rises and sets, the seasons proceed in their expected rhythm. But at a level of precision that requires atomic clocks and decades of careful measurement, there are variations. The length of a day is not constant. It fluctuates by tiny fractions of a second over periods of years and decades, sometimes lengthening, sometimes shortening, responding to processes that redistribute mass and angular momentum within the planet. The atmosphere contributes to these variations. Shifting wind patterns transfer momentum between the air and the solid Earth, causing the rotation rate to speed up or slow down slightly. The oceans play a role as well, through tides and currents, and deep within the planet the core participates in this exchange. Angular momentum, the quantity that describes how much rotational motion a system contains, must be conserved within the Earth as a whole, assuming no external torques act on the planet. If one part of the Earth speeds up, another part must slow down to compensate. The atmosphere can transfer momentum to the crust, altering the day length by milliseconds over the course of a year. The core can do the same, though on longer timescales. If the inner core changes its rotation rate, either accelerating or decelerating relative to the mantle, then the mantle must respond with an opposite change to conserve the total angular momentum. The effect on the surface is subtle, a lengthening or shortening of the day by microseconds per year, far too small to perceive without instruments, but detectable through precise timekeeping systems that compare Earth's rotation against atomic time standards. Some researchers have proposed that variations in day length observed over the past several decades may correlate with changes in the inner core's rotation, though the evidence remains circumstantial and the connection difficult to prove definitively. The magnetic field offers another potential signal. If the inner core's rotation influences the geodynamo, then changes in that rotation might appear as changes in the magnetic field measured at the surface. The field is already known to vary on multiple timescales. The magnetic poles drift, completing irregular loops across the surface over decades and centuries. The field's intensity waxes and wanes, sometimes weakening by 10 or 20% over a few hundred years before recovering. And there are more rapid variations, pulses and jerks in the field, that occur over months or years, thought to arise from sudden changes in the flow patterns of the outer core. Isolating the contribution of the inner core's rotation from all these other sources of variability is extraordinarily difficult. The outer core is a vast and turbulent region, and its dynamics are complex enough to generate magnetic field changes without any involvement of the inner core. Still, the possibility exists that some of the field variations observed over the past few decades reflect the inner core's transition to a different rotational state, a hypothesis that future observations may confirm or refute. What is clear is that the core does not operate in isolation. It is part of a coupled system that includes the mantle, the crust, the oceans, and the atmosphere, all exchanging momentum, heat, and magnetic forces in a web of interactions that span timescales from seconds to billions of years. A change in the core's rotation is not merely an internal adjustment. It is an event, however gradual, that propagates through the system, altering balances and creating new equilibria that may persist for centuries before the next shift occurs. The planet absorbs these changes without drama, integrating them into the slow evolution of its structure and dynamics, but they are real nonetheless, and they remind us that even the deepest, most remote parts of the Earth remain connected to the surface world in ways we are only beginning to understand. The scientists who study the core work within constraints that would seem impossible in almost any other field. They cannot visit their subject. They cannot sample it directly. They cannot run controlled experiments on it. They must rely on signals that travel through thousands of miles of rock, filtered and distorted by every layer they pass through. And from those signals, they must infer not only the structure of the core, but also its dynamics, its history, and its future behavior. The tools they use, seismometers, magnetometers, atomic clocks, supercomputers, are sophisticated, but they are fundamentally limited by the fact that the core does not communicate clearly. It speaks in echoes, in fluctuations, in anomalies that must be teased out of noisy data through years of analysis. And yet, despite these limitations, the picture that has emerged over the past century is remarkably coherent. We know the core is there. We know it is made of iron and nickel. We know it has layers, a liquid outer region and a solid inner sphere. We know it generates the magnetic field. We know it is growing, cooling, changing. These are not speculations. They are conclusions drawn from thousands of independent measurements, cross-checked through multiple methods, validated through models that reproduce the observations. But the coherence of that picture does not imply completeness. Every new generation of instruments, every improvement in computational power, every refinement in analysis techniques reveals details that were previously hidden. The inner core's rotation was not predicted by theory. It was discovered through observation, a surprise that forced scientists to rethink their models and consider mechanisms they had not previously accounted for. The possibility that this rotation has now changed is another surprise, one that has emerged only because researchers have access to decades of seismic data and the tools to analyze it in ways that were not possible when the data were first recorded. The core continues to reveal itself slowly, offering glimpses of its nature through the indirect measurements that are all we have, and each glimpse raises as many questions as it answers. The next generation of observations may clarify whether the inner core's rotation has truly changed, or whether the apparent slowdown is an artifact of incomplete data and imperfect models. New seismic networks are being deployed, new satellites are measuring the magnetic field with unprecedented precision, and new computational models are being developed that simulate the core's behavior in ever greater detail. Over the coming decades, the picture will sharpen, and uncertainties will narrow, though they will never vanish entirely. The core will remain distant, inaccessible, knowable only through inference, but the quality of that inference will continue to improve as long as scientists are willing to listen to the echoes and interpret what they find. Time operates differently in the core. The processes that unfold there do not align with human schedules or even with human lifespans. They are measured instead against the lifespan of the planet itself, against the 4.5 billion years that have passed since Earth coalesced from the disk of dust and gas surrounding the young sun. In that vast span, the formation of the inner core is a relatively recent event, occurring perhaps 1 billion years ago, maybe less. Before that moment, the planet existed without a solid center, its entire core molten and convecting, generating a magnetic field through mechanisms we can only model indirectly. The inner core's appearance marked a threshold, a transition in the planet's thermal evolution, but it was not an event that happened suddenly. The first crystal of solid iron that formed at the center did not announce itself. It simply grew atom by atom, following the thermodynamic logic of pressure and temperature, until it became large enough to influence the dynamics of the surrounding liquid. That process is still happening now, and it will continue for billions of years into the future, assuming the planet survives long enough. The timescales involved are difficult to hold in mind. A billion years is not a duration you can experience or even imagine in any concrete sense. It is a number, an abstraction that represents a stretch of time longer than the existence of complex multicellular life, longer than the oxygenation of the atmosphere, longer than the formation of the oldest rocks still present on the surface. In a billion years, continents have assembled and broken apart multiple times, mountain ranges have risen and eroded away, entire ocean basins have opened and closed. The core during all of this has been cooling, releasing heat into the mantle, driving the convection that powers plate tectonics and volcanism, and gradually solidifying as the temperature at its center drops below the melting point of iron at those pressures. The rate of cooling is slow, governed by the rate at which heat can escape through the mantle, and that rate depends on the mantle's temperature, its viscosity, the pattern of convection within it, and the efficiency of heat transfer at its upper boundary. These are not constants. They change as the planet evolves, creating feedback loops that can accelerate or decelerate the cooling process over geological time. The inner core's rotation, if it is indeed changing, operates within this larger context. The suggestion that the inner core may have slowed or reversed its superrotation is based on observations spanning a few decades, perhaps as much as 60 years, if you include the earliest usable seismic records. 60 years is a meaningful interval on a human timescale, long enough to encompass entire careers, multiple generations of scientific instruments, and significant advances in theory. But 60 years is an instant in the life of the core. It is a single frame in a film that has been running for a billion years and will continue for billions more. The changes we observe may represent the beginning of a longer cycle, or they may be transient fluctuations that will reverse within a century. Or they may be the early stages of a more permanent shift that will define the core's behavior for the next 100,000 years. We do not yet know, because we do not have enough data to see the pattern clearly, and we may not have enough data for generations. This is the challenge of studying planetary interiors. The systems are vast, the timescales are long, and the processes are hidden from direct observation. You can measure the present state with reasonable precision, and you can infer something about the past from the record preserved in rocks and magnetic anomalies. But predicting the future requires understanding mechanisms that may take thousands or millions of years to fully express themselves. The core does not repeat its behavior on convenient timescales. It does not perform experiments that can be reproduced in a laboratory or even within the span of recorded human history. It simply continues, driven by forces that are fundamental and indifferent, evolving according to the laws of physics without regard for whether anyone is watching or attempting to understand. There is a certain humility required in this kind of science. You must accept that the answers you seek may not arrive within your lifetime, that the models you build are provisional, that the observations you make are snapshots of a process so slow that its trajectory may not be discernible even after decades of measurement. You must accept that the planet does not accommodate itself to human curiosity, that it will not speed up or clarify its behavior to make your work easier. The core will do what it does, and you can either attempt to understand it through the limited means available, or you can acknowledge the limits of knowledge and move on. Most scientists working in this field choose the former, dedicating careers to the patient accumulation of data and the incremental refinement of models, knowing that the full picture may never be visible, but that each small improvement brings the understanding closer to reality. The inner core's rotation, then, is not a mystery that will be solved in a single paper or even a single decade. It is a question that will be answered gradually through the collective effort of many researchers analyzing many data sets, cross-checking their findings against independent observations, refining their models as computational power increases and new theoretical insights emerge. The process is slow, as slow as the phenomenon it seeks to understand, and that slowness is not a flaw. It is a reflection of the reality that some questions are worth pursuing, even when the answers take generations to arrive, because the pursuit itself expands the boundaries of what is knowable and deepens the understanding of how planets work at the most fundamental level. And in the meantime, the core continues. It spins or it doesn't, or it spins in ways that vary over time. It grows, adding mass to the solid inner sphere as iron crystallizes out of the molten outer core. It generates magnetic fields, sustaining the geodynamo through the slow churn of convection. It releases heat, contributing to the thermal budget that drives plate tectonics and maintains the planet as a geologically active world. It does all of this without awareness, without intention, without any consideration for the fact that billions of organisms live on the surface, dependent on the stability that the core helps to provide. The core is not a sentinel. It is not a guardian. It is simply a consequence of how matter behaves under extreme conditions, a byproduct of planetary formation and thermal evolution, operating according to principles that were set in motion when the solar system formed, and that will continue until the planet reaches thermal equilibrium with its surroundings, an endpoint so distant that contemplating it feels more like philosophy than science. The magnetic field generated by the core extends far beyond the planet's surface. It stretches into space, forming a region called the magnetosphere that reaches tens of thousands of miles outward on the side facing the sun and trails even farther on the night side, drawn out into a long tail by the solar wind. This is not a static structure. It fluctuates constantly, compressed when the sun is active and erupting with charged particles, expanding when the solar wind weakens. The boundary between the magnetosphere and interplanetary space is called the magnetopause, and it marks the limit of the core's influence in a very direct sense. Beyond that boundary, the sun's magnetic field dominates. Within it, Earth's field prevails, a bubble of influence created by currents flowing in molten metal 2,000 miles beneath the surface. The existence of this field has consequences for the surface, though not in the urgent or immediate ways that popular accounts sometimes suggest. The magnetosphere deflects much of the solar wind, preventing the charged particles streaming from the sun from reaching the atmosphere directly. Without this deflection, the solar wind would interact with the upper atmosphere more intensely, gradually stripping away lighter gases over geological time. This process is not theoretical. It has been observed on Mars, which lacks a global magnetic field and has lost much of its early atmosphere to solar wind erosion over billions of years. Earth retains its atmosphere in part because the magnetic field provides a form of shielding, though the mechanism is complex and involves more than simple deflection. The field channels some particles toward the poles, where they collide with atmospheric gases and produce auroras, those curtains of green and red light that shimmer in the night sky at high latitudes. The auroras are beautiful, but they are also a reminder that the magnetosphere is not an impermeable barrier. It allows some interaction between the solar wind and the atmosphere, just not enough to strip the atmosphere away at rates that would be noticeable over human timescales. Life on Earth exists within the context of this magnetic field, and it is reasonable to wonder whether complex life could have arisen without it. The question is difficult to answer definitively because we have only one example to study, and the history of life on this planet has been shaped by countless factors, each interacting with the others in ways that make isolating any single cause nearly impossible. The magnetic field may have been essential, or it may have been merely helpful, one among many conditions that made the surface habitable. What is certain is that the field has existed for most of Earth's history. Rocks as old as 3.5 billion years preserve magnetic signatures that indicate a geodynamo was already operating when those rocks formed. The field's intensity and structure have varied over time. There have been periods when it was stronger or weaker, periods when the poles reversed and the field temporarily weakened during the transition, but it has persisted. This persistence reflects the fact that the core remains hot, convecting and capable of sustaining the dynamo process. As long as the outer core is liquid and in motion, the field will continue to exist. And as long as the planet continues to cool and the inner core continues to grow, the conditions necessary for convection will be maintained. The field, then, is not a protective shield in the sense that implies active defense or intentionality. It is a consequence of the core's thermal and compositional state, a byproduct of the planet's ongoing evolution. The fact that it happens to deflect solar wind and reduce atmospheric erosion is not a design feature. It is an outcome, one that has influenced the trajectory of Earth's history, but that could have been otherwise if the planet had formed differently or cooled at a different rate. Mars had a magnetic field early in its history, generated by a dynamo that operated when its core was still molten and convecting vigorously. But Mars is smaller than Earth, and it cooled faster. Its core solidified, or at least ceased to convect efficiently enough to sustain a dynamo, and the global magnetic field disappeared, leaving only the remnant magnetism frozen into ancient crustal rocks. The absence of that field has contributed to Mars becoming the cold, dry, airless world it is today. But the loss was gradual, occurring over hundreds of millions of years, not as a catastrophic event, but as the slow fading of a process that could no longer be sustained as the planet's interior cooled. Earth's core, by comparison, remains vigorous. The outer core is still molten, still convecting, still generating magnetic fields through the motion of electrically conducting fluid. The inner core continues to grow, releasing latent heat and buoyant material that drives convection in the outer core. The system is not in equilibrium because the planet is still cooling, but it is stable enough to have persisted for billions of years and will persist for billions more. The magnetic field is not weakening in any long-term sense, despite periodic fluctuations. The geodynamo is not failing. The core is not solidifying. These are processes that will eventually happen, but they are so far in the future that they belong to a different epoch of planetary evolution, one in which the Sun itself will have changed significantly and the surface environment will be unrecognizable. The connection between the core and habitability, then, is real but indirect. The core does not protect life in any active way. It does not respond to threats or adjust its behavior to maintain conditions favorable to organisms. It simply continues to do what it does, and the magnetic field it generates happens to reduce the rate at which the solar wind erodes the atmosphere, and that reduction over geological time has allowed the atmosphere to remain thick enough to support liquid water on the surface and to provide pressure and insulation against the cold of space. Life, in turn, has modified the atmosphere, adding oxygen and other gases that would not be present in significant quantities on a lifeless world, and those modifications have further shaped the environment in ways that feed back into the conditions that allow life to persist. The system is interconnected, but it is not coordinated. The core does not know about life, and life does not influence the core. They coexist, separated by thousands of miles of rock, each following its own trajectory according to the laws that govern physical and biological processes, and the fact that they have remained compatible for billions of years is as much a consequence of the planet's initial conditions and its location in the solar system as it is of any particular mechanism or feedback. Still, there is something profound in the realization that the deepest part of the planet, the part most removed from the surface and most alien in its conditions, contributes to the stability that makes the surface habitable. The core does not care, but its existence matters. Its heat drives plate tectonics, which recycles carbon and regulates the climate over geological time. Its magnetic field reduces atmospheric loss, preserving the thin envelope of gas that allows life to exist. Its slow cooling sets the timescale for planetary evolution, determining how long Earth will remain geologically active and capable of supporting a complex biosphere. These are not minor contributions, they are fundamental, woven into the structure of the planet in ways that cannot be separated without changing everything. Between the core and the mantle lies another boundary, another transition where properties change and processes meet. The core-mantle boundary sits nearly 1,800 miles beneath the surface, marking the interface between the liquid iron of the outer core and the solid rock of the lower mantle. This boundary is not as dramatic in its physical contrast as the boundary between liquid and solid within the core itself, but it is no less significant. On one side, iron at temperatures exceeding 4,000 degrees Celsius flows in currents driven by heat and buoyancy. On the other side, rock compressed under enormous pressure remains solid but capable of flowing slowly over geological time, convecting in patterns that carry heat from the interior toward the surface. The two materials, iron and rock, have different densities, different thermal properties, different responses to pressure and temperature. Where they meet, heat flows from the hotter core into the cooler mantle, and that heat flow drives much of the mantle's convection, which in turn powers plate tectonics and volcanic activity at the surface. The core-mantle boundary is not smooth. Like the boundary between the outer and inner core, it has topography, variations in height that can reach several miles. These variations are not random. They reflect the structure of the mantle above, the distribution of heat within the core, and the long-term pattern of convection that has shaped both regions over hundreds of millions of years. In some places, the boundary dips downward, where cold material from the surface has descended through the mantle and accumulated, forming dense piles that push into the core. In other places, the boundary rises, where hot material from the core has heated the overlying mantle and caused it to become buoyant. These topographic features are detected through seismic studies, through the way that waves passing near the boundary are delayed or advanced by tiny fractions of a second, anomalies that accumulate into a picture of a rough and variable interface between two of the planet's largest reservoirs of heat and mass. The heat escaping from the core is not uniform. Some regions of the core mantle boundary conduct heat more efficiently than others, creating patterns that influence how the mantle convects and how the outer core flows. These patterns are thought to affect the geodynamo, imprinting structure on the magnetic field that can be measured at the surface. There is evidence, for instance, that the magnetic field is stronger in certain regions and weaker in others, and that these variations persist over timescales of centuries or longer, suggesting they are rooted in the deep structure of the core and mantle rather than being transient fluctuations. The core and mantle, despite being separated by a boundary, are not independent. They influence each other continuously, exchanging heat and momentum, each shaping the behavior of the other through mechanisms that operate over millions of years. The mantle itself convects slowly, driven by the heat it receives from below and by the heat it generates internally through the decay of radioactive elements. The convection is not rapid. The rock flows at rates measured in centimeters per year, comparable to the speed at which fingernails grow. But that motion, sustained over geological time, is sufficient to transport enormous amounts of heat and to drive the movement of tectonic plates at the surface. The convection patterns are complex, organized into large-scale circulation cells that can persist for tens or hundreds of millions of years before reorganizing in response to changes in boundary conditions or internal structure. The descending limbs of these cells are the cold slabs of oceanic lithosphere that sink at subduction zones, plunging back into the mantle after spending millions of years at the surface. The ascending limbs are the hot plumes that rise from the deep mantle, sometimes reaching the surface and producing volcanic hotspots like Hawaii or Iceland. These plumes may originate at or near the core mantle boundary, where the temperature contrast is greatest and where heat from the core can collect and create instabilities that eventually rise through the overlying mantle. The connection between the core's behavior and the mantle's convection is not straightforward. Changes in the core's heat output or in the pattern of heat flow at the boundary can influence mantle convection, but the mantle responds slowly, taking millions of years to adjust to new conditions. Similarly, changes in mantle convection can affect the core by altering the temperature distribution at the boundary, which influences the pattern of convection in the outer core and the forces acting on the inner core. The coupling between the two regions is real, but it operates on timescales so long that cause and effect become difficult to separate. A change in the core might produce a response in the mantle that feeds back into the core only after millions of years, by which time other factors have also changed, complicating any attempt to isolate individual mechanisms. The heat that drives all of this motion comes from two sources. The first is primordial heat, the residual thermal energy left over from the planet's formation, when countless collisions of planetesimals and protoplanets released gravitational potential energy as heat. The Earth formed hot, with surface temperatures high enough to melt rock, and it has been cooling ever since, radiating that heat into space at a rate determined by the thermal properties of the mantle and crust. The second source is radiogenic heat, produced by the decay of unstable isotopes like uranium, thorium, and potassium that were incorporated into the planet's material when it formed. These isotopes decay slowly, releasing energy that adds to the thermal budget and slows the rate of cooling. The balance between heat loss and heat production determines how quickly the planet cools, and that rate, in turn, determines how long the core remains molten, how long the inner core continues to grow, and how long the geodynamo can sustain the magnetic field. Current estimates suggest the Earth is losing heat faster than it produces it through radioactive decay, meaning the planet is gradually cooling and will continue to cool for billions of years. But the rate is slow, and the thermal inertia of the planet is enormous. The core contains vast reserves of heat, and releasing that heat through the mantle is a process constrained by the thermal conductivity of rock and the efficiency of convection. Even if the core were to stop producing heat entirely, it would take billions of years for it to cool to the point where the outer core solidifies and the geodynamo ceases. The timescale is so long that it extends beyond the expected lifetime of the Sun as a stable star, beyond the point at which the Sun will begin to expand and eventually engulf the inner planets. The core's cooling, then, is not something that will end the planet as we know it. Other processes external to the Earth will intervene long before the core runs out of heat. In the meantime, the core continues to release its energy, driving convection in the outer core, sustaining the magnetic field, contributing to mantle convection, and maintaining the planet as a geologically active world. The process is self-regulating in the sense that the rate of cooling depends on the rate of heat loss, and the rate of heat loss depends on the efficiency of convection in the mantle, which in turn depends on the temperature gradient between the core and the surface. As the planet cools, the temperature gradient decreases, and convection becomes less vigorous, which slows the rate of cooling, creating a negative feedback that extends the timescale over which the core remains molten. The system is not static, but it changes slowly, adjusting to new conditions over timescales that dwarf human history and that challenge our ability to conceptualize duration. The magnetic field has reversed its polarity many times in Earth's history. North becomes south, south becomes north, and the process unfolds over a period that may last anywhere from a few hundred to several thousand years. The most recent reversal occurred roughly 780,000 years ago, a transition recorded in volcanic rocks and sediments that preserve the orientation of the magnetic field at the time they formed. Before that reversal there was another, and before that another, stretching back through geological time in an irregular sequence with no obvious pattern. Sometimes reversals happen frequently, with several occurring within 1 million years. Sometimes the field remains stable for tens of millions of years without reversing at all. The longest known period of stability, called the Cretaceous Normal Superchron, lasted nearly 40 million years, from about 120 million years ago to 80 million years ago, a span during which the magnetic field maintained the same polarity even as continents drifted. Dinosaurs evolved and diversified, and flowering plants spread across the land. The cause of magnetic reversals lies in the dynamics of the outer core. The geodynamo is not a perfectly stable system. It operates in a regime where small perturbations can grow, where flow patterns can reorganize, where the magnetic field generated by one configuration of currents can feed back into the fluid motion and alter it. Reversals are thought to occur when the balance of forces within the core shifts in such a way that the existing magnetic field weakens and a new field with opposite polarity emerges to take its place. The process is not instantaneous. During a reversal, the field becomes more complex, with multiple magnetic poles appearing at the surface, sometimes more than 2 at once, and the overall intensity of the field decreases, sometimes to a small fraction of its normal strength. This weakened state may persist for centuries before the new configuration stabilizes and the field regains its strength. The geodynamo does not fail during a reversal. It continues to operate, but it produces a different pattern, a temporary state that eventually gives way to a new stable polarity. Life has survived every magnetic reversal that has occurred since complex organisms appeared on Earth. There is no evidence in the fossil record of mass extinctions coinciding with reversals, no indication that the weakening of the magnetic field during the transition caused widespread harm to ecosystems or drove species to extinction. This is not to say that reversals have no effects. During the period when the field is weak and disorganized, the magnetosphere is less effective at deflecting solar wind, and the flux of charged particles reaching the upper atmosphere increases. This could, in principle, affect the chemistry of the stratosphere, alter the production of certain isotopes that form when cosmic rays interact with atmospheric gases, or increase the radiation dose received by organisms at high altitudes or high latitudes. But these effects, if they occur, are subtle and short-lived compared to the other environmental changes that organisms routinely experience. Climate fluctuations, volcanic eruptions, asteroid impacts, sea level changes, all of these have had far greater impacts on life than magnetic reversals, and life has proven resilient to all of them. The regularity with which reversals occur, or rather the lack of regularity, suggests that they are not driven by external forces, but emerge from the internal dynamics of the core. There is no cycle, no predictable interval that would allow scientists to forecast when the next reversal will happen. The magnetic field is currently weaker than it has been at many times in the past, and the rate of weakening has accelerated slightly over the past few centuries, leading some to speculate that a reversal may be approaching. But the field has weakened and recovered many times without reversing, and the current weakening may simply be part of the natural variability that the geodynamo exhibits over centuries and millennia. Predicting a reversal from the present state of the field is like trying to predict the weather months in advance. There are too many variables, too much chaos in the system for certainty to be possible. If a reversal were to begin, it would not be catastrophic. The transition would unfold over a timescale long enough that human societies could adapt, assuming they were aware of it and understood what was happening. Navigation systems that rely on the magnetic field, such as compasses, would become unreliable as the field weakened and the pole positions wandered. But modern navigation relies more on satellites and GPS than on compasses, and those systems would continue to function. Electrical grids and communication networks might experience increased disruptions from space weather events, as the weakened magnetosphere allows more solar particles to reach the atmosphere, but these are engineering challenges, not existential threats. The atmosphere would not be stripped away, the surface would not be sterilized by radiation. Life would continue, as it has through every previous reversal, largely unaware that anything fundamental had changed. The connection between magnetic reversals and the inner core's rotation is uncertain. Some models suggest that changes in the inner core's rotation could influence the stability of the geodynamo and potentially trigger reversals, though the mechanisms are not well understood. Other models suggest that reversals are driven primarily by processes in the outer core and that the inner core plays only a minor role. The evidence is insufficient to favor one hypothesis over the other, and it is possible that both are correct to some degree, that reversals arise from a combination of factors, including changes in the outer core's convection pattern, variations in heat flow at the core mantle boundary, and shifts in the inner core's rotation or growth rate. The system is complex enough that multiple pathways to reversal may exist, and which pathway dominates in any given reversal may depend on the specific conditions present at that time. What is clear is that reversals are a normal part of the magnetic field's behavior, an expression of the geodynamo's inherent variability rather than a sign of malfunction or instability. The field has reversed hundreds of times over the planet's history, and it will reverse many more times in the future, assuming the core remains molten and convecting. Each reversal is unique in its details: how long it takes, how weak the field becomes, what pattern of magnetic poles appears during the transition, but the overall phenomenon is consistent. The geodynamo is capable of producing stable magnetic fields with either polarity, and it switches between them on timescales that are short compared to the age of the planet, but long compared to human lifetimes. The possibility that the inner core's rotation is changing adds another layer to this picture, another variable that may influence the geodynamo's behavior in ways we have not yet fully accounted for. If the inner core's rotation does cycle, speeding up and slowing down over periods of decades or centuries, then that cycle may modulate the strength or stability of the magnetic field, creating patterns that are detectable at the surface but that do not rise to the level of triggering a reversal. Or the rotation changes may be more directly involved in the reversal process, altering the flow patterns in the outer core in ways that destabilize the existing magnetic configuration and allow a new one to emerge. These are questions that will require more data, more modeling, and more time to answer. But they are questions worth asking because they speak to the fundamental nature of how planets generate and sustain magnetic fields and how those fields evolve over time. Other planets offer perspective on Earth's core, though the comparison is limited by how little we know about their interiors. Mars, as mentioned, once had a magnetic field generated by a core dynamo, but that field disappeared billions of years ago when the planet's interior cooled enough that convection in the core ceased or became too weak to sustain the dynamo process. The evidence for this early field is preserved in the ancient crust, where rocks retain the magnetization they acquired when they formed in the presence of a global magnetic field. Younger rocks show no such magnetization, indicating that the field had already vanished by the time they solidified. Mars today has only localized magnetic anomalies, remnants of that early field frozen into the crust, and these remnants are among the strongest crustal magnetic fields measured anywhere in the solar system, suggesting that the Martian dynamo was vigorous while it operated. But the planet is smaller than Earth, with a lower internal heat budget, and it cooled faster. Its core may still be partially molten, but it no longer convects vigorously enough to generate a magnetic field, and without that field, the solar wind has gradually stripped away much of the atmosphere that Mars once possessed, transforming it from a potentially habitable world with liquid water on its surface into the cold, dry desert it is today. Venus, by contrast, is nearly the same size as Earth, and presumably has a similar internal structure, with an iron core that should be comparable in temperature and composition to Earth's. Yet Venus has no global magnetic field, or if it does, the field is so weak that it has not been detected by spacecraft that have orbited or descended through the planet's atmosphere. The absence of a Venusian magnetic field is puzzling. The planet should have a molten core, and it should have the internal heat necessary to drive convection, yet no dynamo appears to be operating. One explanation is that Venus rotates too slowly. The planet takes 243 Earth days to complete a single rotation, and the slow rotation may reduce the Coriolis forces that help organize convection in the core into the patterns necessary for dynamo action. Without sufficient rotation, the fluid motions in the core may be too disorganized or too weak to generate a self-sustaining magnetic field. Another possibility is that the core is still fully molten without a solid inner core, and that the presence of an inner core is necessary for the dynamo to operate efficiently. Earth's inner core provides a boundary that helps organize the flow patterns in the outer core, and it releases latent heat and buoyant material as it grows, both of which contribute to driving convection. If Venus lacks an inner core, its dynamo may be less effective, or it may have shut down entirely despite the core remaining molten. The question remains unresolved, a reminder that having the right ingredients does not guarantee the same outcome. Mercury, the smallest of the rocky planets, does have a magnetic field, albeit a weak one, only about 1% the strength of Earth's field. The existence of any field at all is surprising, given the planet's size and the expectation that such a small body should have cooled rapidly and solidified its core long ago. The discovery of Mercury's magnetic field suggests that its core is at least partially molten and capable of sustaining some form of dynamo, though the details of how this works remain unclear. The planet may have a large iron core relative to its size, and the cooling may have been slowed by an insulating layer of silicate mantle, allowing the core to remain hot enough to generate a field even billions of years after the planet formed. Or the dynamo may operate in a different regime than Earth's, driven by compositional convection rather than thermal convection, with lighter elements released as the core slowly solidifies, providing the buoyancy needed to sustain fluid motion. The field is weak enough that it offers little protection from the solar wind, and Mercury's thin atmosphere is constantly being stripped away and replenished by processes that depend on the planet's proximity to the Sun. But the field exists, and its existence expands the range of conditions under which planetary dynamos can operate. The gas giants, Jupiter and Saturn, also have magnetic fields, far stronger than Earth's, generated by dynamos operating in entirely different materials. Jupiter's magnetic field is generated not in a molten iron core, but in a layer of metallic hydrogen, a form of hydrogen that exists under such extreme pressures that the electrons are no longer bound to individual atoms and can move freely, allowing the material to conduct electricity like a metal. This layer lies deep within the planet, beneath an ocean of molecular hydrogen and helium thousands of miles thick, and it convects vigorously, driven by the immense heat escaping from Jupiter's interior. The resulting magnetic field is enormous, extending millions of miles into space and trapping charged particles in radiation belts far more intense than Earth's. Saturn's magnetic field is generated by a similar process, though the field is somewhat weaker and more symmetric than Jupiter's. The existence of these fields demonstrates that dynamos are not unique to rocky planets with iron cores, that the fundamental process, convection of electrically conducting fluid in a rotating body, can operate in a wide range of environments and materials. What these comparisons reveal is that magnetic fields are common but not universal among planets, and that the presence or absence of a field depends on a combination of factors including the planet's size, its rotation rate, its internal structure, and its thermal history. Earth occupies a particular point in this parameter space, one where the conditions are favorable for a strong, stable dynamo that has operated for billions of years. But the system is not guaranteed. Mars shows that dynamos can shut down when planets cool too much. Venus suggests that slow rotation or the absence of an inner core may inhibit dynamo action even in planets that should otherwise be capable of generating fields. Mercury demonstrates that even small planets can sustain weak dynamos under the right conditions. And the gas giants remind us that the dynamo process is more general than any specific planetary configuration, that it is a consequence of fundamental physics rather than a feature unique to Earth-like worlds. The study of planetary magnetic fields, then, is not just about understanding Earth. It is about understanding how planets work, how they evolve, and how the presence or absence of a magnetic field influences their long-term habitability. Earth's core is unique in its details, but the principles that govern its behavior apply more broadly to other worlds in this solar system and to the rocky planets orbiting distant stars that we are only now beginning to detect and characterize. Some of those planets will have magnetic fields, and some will not, and the differences will shape their atmospheres, their surface conditions, and their potential to support life. The core, in this sense, is not just a feature of Earth. It is a key variable in the equation that determines what kind of world a planet becomes, and studying it here provides insights that extend far beyond this single example. And yet, for all the comparisons and all the models, Earth's core remains the only one we can study in any detail, the only one where we have decades of seismic data and centuries of magnetic field observations, and the accumulated knowledge of generations of scientists who have dedicated their careers to interpreting those signals. The cores of other planets are even more remote and inaccessible than Earth's, known only through brief flybys or orbital observations that provide hints but never direct confirmation. Earth's core, for all its mystery, is the standard against which all other planetary cores are measured, the reference point that defines what we think we know about how dynamos work and how planets evolve. There is a particular quality to knowledge built from echoes. It is not the direct, tactile understanding that comes from holding an object in your hand, turning it over, examining its surface and weight and texture. It is instead a kind of inference, a reconstruction built from signals that have traveled through unknown territory and arrived transformed by their journey. When you study the core through seismology, you are not seeing the core. You are seeing the shadow it casts in the travel times of earthquake waves, the way those waves bend and slow and speed up as they pass through different materials. The picture you construct is real. It corresponds to something that exists, but it is also mediated, filtered through layers of interpretation and assumption, and it can never be as complete or as certain as a photograph or a direct measurement would be. This does not make the knowledge invalid. It makes it provisional, subject to revision, dependent on the quality of the data and the sophistication of the models used to interpret it. Every seismometer that records an earthquake contributes a single data point, a measurement of when a wave arrived and how strong it was. Thousands of these data points, accumulated over decades, allow scientists to construct tomographic images of the interior, maps that show where the mantle is hotter or cooler, where the core is denser or less dense, where boundaries are smooth or rough. But the resolution is limited. The waves do not sample the interior uniformly. Some regions are crossed by many wave paths, and those regions are well constrained. Other regions are sampled rarely, and the images there are blurrier, more uncertain. The core is relatively well sampled because waves from earthquakes on one side of the planet often pass through it on their way to seismometers on the opposite side. But even so, the details remain elusive. Small structures, variations on scales of a few kilometers, are invisible. Only large features, differences that extend over hundreds or thousands of kilometers, can be resolved. The process of turning seismic data into images of the core is not straightforward. It requires solving an inverse problem, where you start with observations at the surface and work backward to infer what structure deep inside the planet could have produced those observations. Inverse problems are notoriously difficult because they are often underdetermined. Many different internal structures could produce the same surface observations, and choosing among them requires additional assumptions or constraints. Scientists use models of how seismic waves travel through different materials, based on laboratory experiments and theoretical calculations, to predict what the data should look like for a given internal structure. They then adjust the structure iteratively, comparing the predicted data to the observed data until the two match as closely as possible. The process is computationally intensive and requires careful attention to sources of uncertainty, but it works. The models that emerge are consistent with the data and with each other, at least within the limits of resolution, and they provide a framework for understanding the core's properties and behavior. Still, there is always the possibility of error, of misinterpretation, of structures or processes that the current models do not account for. The suggestion that the inner core's rotation has changed is a reminder of this. The evidence comes from comparing seismic wave travel times recorded decades apart, looking for shifts that could indicate the inner core has rotated relative to the surface. But interpreting those shifts requires assuming that the structure of the inner core is stable over time, that the anomalies being tracked are not themselves changing, and that the wave paths are being sampled consistently. If any of these assumptions are wrong, the conclusions could be misleading. Some researchers have questioned whether the observed changes in travel times reflect rotation at all, suggesting instead that they could be caused by changes in the structure of the inner core, by variations in how waves are generated or recorded, or by artifacts in the data processing. The debate is ongoing, and it reflects the inherent difficulty of extracting definitive answers from indirect measurements. This uncertainty is not a failure. It is the condition under which all deep Earth science operates. You cannot visit the core. You cannot run controlled experiments on it. You cannot even observe it continuously. You must work with what the planet gives you, seismic waves from earthquakes that occur unpredictably, magnetic field measurements that integrate signals from the entire geodynamo, laboratory experiments that approximate but cannot fully replicate core conditions. From these fragments you build a picture, always aware that the picture is incomplete, always prepared to revise it when new data arrive. The process requires patience, humility, and a willingness to live with ambiguity, qualities that are not always celebrated in a culture that values certainty and immediate answers, but that are essential for making progress in areas where certainty is not available. The scientists who study the core are comfortable with this ambiguity, or at least they have learned to be. They understand that their conclusions are always tentative, that today's model may be superseded by tomorrow's, that the questions they are asking may take decades or generations to answer fully. They publish their results, knowing that other researchers will scrutinize them, challenge them, attempt to replicate or refute them using different methods or different data sets. This is how science advances, through the gradual accumulation of evidence and the continual testing of hypotheses against new observations. The process is slow, often frustrating, and sometimes contentious, but it is also remarkably effective at converging on truths that are robust and reliable, even if they are never final. The core, in this sense, is a mirror for the scientific process itself. It is a system that does not reveal itself easily, that requires persistence and ingenuity to study, that rewards careful observation and punishes hasty conclusions. It is a reminder that the natural world does not organize itself for human convenience, that understanding it requires effort and creativity, and a willingness to accept that some questions may remain open for a very long time. The core does not care whether we understand it. It continues to exist, to evolve, to generate magnetic fields and release heat, indifferent to our observations and our models. Our understanding of it is a human construct, built from the tools and concepts we have developed over centuries of inquiry, and it is no less valuable for being incomplete. And yet there is something profound in the effort itself, in the fact that humans, living on the surface of a planet, have found ways to peer into its deepest interior and make sense of what they find there. The core is as remote from everyday experience as any astronomical object, yet it is part of the same world we inhabit, hidden beneath our feet, influencing the conditions that make life possible, operating according to principles that we can investigate and understand, at least partially, using the methods of observation and reasoning that define scientific inquiry. The distance between the surface and the core is not merely physical. It is epistemological, a gap between what is directly accessible and what must be inferred, and the fact that this gap can be bridged, however imperfectly, is a testament to the power of indirect observation and the human capacity for abstract thought. The Earth you walk on is not the Earth that exists in its entirety. The surface, the continents and oceans, the mountains and valleys, the atmosphere and biosphere, is a thin shell, a boundary layer between the planet's interior and the vacuum of space. Everything you can see and touch and experience directly represents less than 1% of the planet's mass. The other 99% lies below, hidden beneath thousands of miles of rock and metal, inaccessible and largely unknowable except through the indirect methods that science has developed over the past century. And yet, that hidden majority is not inert. It is in motion, convecting, cooling, changing, generating forces that reach the surface and shape the conditions under which life exists. The core, the mantle, the deep interior, they are not separate from the world you inhabit. They are continuous with it, part of the same system, operating according to the same physical laws, connected through processes that span the full diameter of the planet. This continuity is easy to forget. Daily life unfolds entirely at the surface, in the narrow zone where rock meets air and water, where temperatures are moderate enough to support liquid water and complex chemistry, where sunlight provides energy that drives ecosystems and weather. The core does not announce itself. It does not intrude on consciousness. You do not feel its heat or its rotation or the magnetic field it generates, not directly. The ground beneath your feet feels solid and stable, unchanging from day to day, and the sky above feels like a permanent feature, not a thin envelope of gas held in place by gravity and protected by a magnetic field rooted in molten metal thousands of miles below. The illusion of separateness is strong, reinforced by the fact that the surface world is where all observable change occurs, where storms gather and dissipate, where seasons turn, where organisms are born and die and evolve. The deep interior, by contrast, seems static, frozen, irrelevant to the processes that matter to living things. But the illusion is just that, an illusion born of the mismatch between human timescales and geological timescales. The core is not static. It is changing constantly, just slowly, at rates that require decades or centuries or millennia to become apparent. The magnetic field drifts and fluctuates. The inner core grows, adding mass as the planet cools. The convection patterns in the outer core shift, altering the balance of forces that drive the geodynamo. The heat flowing from the core into the mantle varies, influencing the vigor of mantle convection and, ultimately, the activity of plate tectonics at the surface. All of this is happening now, has been happening throughout human history, and will continue long after any record of human civilization has been erased. The core is not a static foundation on which the surface rests. It is a dynamic system, evolving on its own timescale, indifferent to the rapid changes that characterize the surface, but no less real for its slowness. The fact that these processes are invisible to ordinary perception does not diminish their importance. The magnetic field generated by the core deflects the solar wind and reduces the rate at which the atmosphere is lost to space. Without it, Earth might have followed a trajectory similar to Mars, gradually losing its atmosphere and becoming inhospitable to life. The heat escaping from the core drives plate tectonics, which recycles carbon between the surface and the interior, regulating the climate over geological time and maintaining conditions compatible with liquid water. Without that heat flow, the planet's surface might have frozen into a static shell with no volcanism, no mountain building, no renewal of nutrients through the recycling of oceanic crust. The core, then, is not incidental to habitability. It is foundational, a prerequisite for the kind of active, dynamic planet that can support complex life over billions of years. Yet this foundation operates without awareness, without intention, without any consideration for the life it supports. The core does not know that organisms exist on the surface. It does not adjust its behavior to maintain favorable conditions. It simply follows the laws of thermodynamics and fluid dynamics, releasing heat because it is hotter than its surroundings, generating magnetic fields because electrically conducting fluid is in motion, cooling because the second law of thermodynamics demands that heat flow from hot to cold until equilibrium is reached. If life benefits from these processes, it is because life has evolved in the context of a planet where these processes occur, adapting to the conditions they create rather than those conditions being tailored to life's needs. The relationship is not one of design, but of compatibility, a fortunate alignment between the planet's internal dynamics and the requirements for habitability that has persisted for billions of years, but that was never guaranteed and could, in principle, break down if the core's behavior changes in ways that alter the surface environment too drastically. The possibility that the inner core's rotation is changing fits into this larger picture of continuity and slow transformation. If the change is real, it represents a shift in one component of the planet's internal machinery, a redistribution of momentum between different layers, an adjustment to new balances of force. But the shift does not threaten the system as a whole. The geodynamo continues, the magnetic field persists, the heat flow remains sufficient to drive mantle convection. The surface experiences no disruption, no sudden deterioration of conditions. Life continues, unaware that anything deep within the planet has changed, because the change, however significant in terms of the physics involved, occurs at a level removed from the processes that directly affect the surface environment. This is the nature of planetary-scale systems. They are robust, capable of absorbing internal changes without collapsing, able to maintain overall stability even as individual components shift and evolve. There is a comfort in this robustness, a reassurance that the planet is not fragile in the way that individual organisms are fragile, that it does not depend on every detail being exactly right to continue functioning. The core can change its rotation, the magnetic field can weaken or reverse, the mantle can reorganize its convection patterns, and the planet as a whole adapts, finding new equilibria that preserve the essential conditions for habitability. This does not mean the planet is invulnerable. External factors, asteroid impacts, changes in solar output, the eventual evolution of the Sun toward a red giant, can alter conditions drastically, potentially rendering the surface uninhabitable. And human activity, operating on timescales far shorter than geological processes, has demonstrated a capacity to change the surface environment in ways that may not be compatible with the continuation of complex ecosystems. But the internal processes, the machinery of the deep Earth, are resilient. They have operated for billions of years, and they will continue to operate for billions more. largely indifferent to what happens at the surface. To live on this planet, then, is to live on a world that is both stable and changing, both familiar and alien. The surface is home, the environment that shaped human evolution and that continues to shape human experience. But the surface is also a thin interface, a boundary between the solid planet and the near vacuum of space, sustained by processes that occur far below and far above, in regions that are inaccessible to direct experience, but that are no less real for their remoteness. The core is one of those regions, perhaps the most remote, certainly among the most influential, a sphere of molten and solid metal at the center of everything, spinning in darkness, generating forces that reach across the diameter of the planet and beyond, operating according to principles that were established billions of years ago, and that will persist until the planet itself ceases to exist as a coherent body. Imagine waiting for the inner core to complete a single additional rotation relative to the surface. If the super-rotation rate suggested by early studies were accurate, a fraction of a degree per year, you would need to wait several centuries to witness a full rotation. Several centuries. Longer than any nation has existed in its current form, longer than any language has remained stable, longer than any written record has survived without interpretation and translation. The human mind is not equipped to perceive change on this timescale. We are creatures of hours and days, of seasons and years, perhaps of decades if we are fortunate and attentive. But centuries exceed the bounds of individual memory and experience. They belong to history, to the accumulated records of many generations, to processes that can be understood intellectually but never felt directly. And yet, this is the pace at which the core operates. Not slowly in any absolute sense. The forces involved are immense, the energies astronomical, but slowly relative to the rhythm of surface life. A change that takes decades to complete is, for the core, practically instantaneous. A process that unfolds over millennia is routine, unremarkable, well within the range of normal variability. The core does not hurry. It has no reason to. It is not responding to threats or opportunities that require rapid action. It is simply evolving according to the physics of heat flow and rotation and magnetic induction, moving from one state to another along a trajectory determined by its initial conditions and the laws that govern matter under extreme pressure and temperature. This disconnect between human timescales and geological timescales is one of the central challenges of Earth science. You can measure the present state of the planet with reasonable precision. You can infer something about the past from the record preserved in rocks and ice and sediments, but understanding how the planet changes requires connecting those snapshots across intervals that may span millions of years, identifying trends and patterns that emerge only when viewed from sufficient temporal distance. It is like trying to understand the plot of a film by watching a single frame every few months. You might eventually piece together the story, but the experience is fragmentary, disjointed, and much of the subtlety is lost. The core presents an extreme version of this problem. It is not only hidden from view, but also changing at a pace that makes real-time observation effectively impossible. The seismic data that suggests changes in the inner core's rotation span several decades, which sounds like a long time, but is barely a blink in the life of the core. It is possible that what we are observing is a temporary fluctuation, a brief deviation from some longer-term average that will reveal itself only after centuries of continuous monitoring. Or it could be the beginning of a more sustained change, a shift in the core's behavior that will persist for millennia and eventually leave a detectable signature in the geological record. Distinguishing between these possibilities requires patience, continued observation, and a willingness to accept that definitive answers may not arrive within any single scientist's career. The concept of geological time was itself difficult for science to accept. For much of human history, the age of the Earth was thought to be measured in thousands of years, not billions. The idea that mountains could rise and erode away, that oceans could open and close, that entire continents could drift across the surface, all of this seemed implausible because the timescales required were so far beyond human experience that they defied intuition. It was only in the 19th and 20th centuries, as evidence accumulated from geology, paleontology, and eventually radiometric dating, that the true age of the planet became clear. 4.5 billion years. A number so large that it loses meaning, that can be written but not truly comprehended, that forces a complete recalibration of how we think about change and stability. Once that timescale is accepted, once you internalize the idea that the planet has existed for billions of years and will continue for billions more, the core's behavior becomes more comprehensible, or at least less alien. A process that takes 1,000 years is fast. A change that unfolds over 1 million years is noticeable. A cycle that repeats every 100 million years is frequent. The core is not sluggish or slow. It is operating at the natural pace of planetary processes, the pace dictated by the rate at which heat can diffuse through rock, the rate at which convection can redistribute material, the rate at which gravitational and magnetic forces can alter the motion of vast masses of fluid and solid metal. From the core's perspective, if it could be said to have a perspective, its behavior is entirely normal, unremarkable, consistent with the dynamics of a cooling planet. From the human perspective, the core's behavior is almost invisible. You cannot watch it happen. You cannot feel it or hear it or sense it in any direct way. You can only infer it from measurements that require sophisticated instruments and decades of patient observation to reveal patterns. This is not a failure of perception. It is a consequence of the mismatch between the timescales on which humans and planets operate. Humans live fast, compressed lives measured in decades, experiencing the world through senses that are tuned to detect changes on timescales of seconds to years. Planets live slow, extended existences measured in billions of years, evolving according to processes that are imperceptible on human timescales, but that are no less real for their slowness. The realization that the core may be changing, that its rotation may have slowed or reversed, forces an acknowledgement of this mismatch. The change, if it is happening, is real. It involves the redistribution of angular momentum across the entire planet. It reflects shifts in the forces acting within the core, changes in the geodynamo, variations in the coupling between the inner core and the outer core and the mantle. But it is happening slowly, at a pace that renders it invisible to anyone who is not actively looking for it, using instruments specifically designed to detect variations in seismic wave travel times or day length or magnetic field structure. The core does not announce its changes. It does not send signals that are obvious or easy to interpret. It simply continues, and those who wish to understand it must meet it on its own terms, must develop methods sensitive enough to detect processes that unfold over decades and centuries, must accept that the answers they seek will arrive slowly, if they arrive at all. This is the reality of studying the deep Earth. You're observing a system that is indifferent to observation, that operates on timescales that exceed human lifespans, that reveals itself only through signals that must be extracted from noise through years of careful analysis. The work requires patience, persistence, and a kind of intellectual humility that acknowledges the limits of what can be known at any given moment. But it also offers a perspective that is rare and valuable, a glimpse into processes that are fundamental to how planets work, that have shaped the history of this world and will shape its future, that connect the deepest interior to the surface in ways that are invisible but essential. The core is changing, perhaps, and that change is worth understanding, not because it poses any immediate threat or offers any immediate benefit, but because it deepens the picture of what the Earth is and how it evolves, and because that understanding is its own reward. The models scientists build of the core are not the core itself. They are representations, constructions made from mathematics and data, and assumptions about how matter behaves under conditions that cannot be fully reproduced in any laboratory. A model can be accurate, in the sense that it reproduces the observations and makes predictions that are borne out by subsequent measurements. But it remains a model, a simplification of a reality that is vastly more complex and detailed than any set of equations can capture. The core has a temperature at every point, a density at every point, a velocity field that describes how the fluid is moving at every instant. It has crystal structures in the inner core that are aligned in certain directions, boundaries that have roughness and topography on multiple scales, convection patterns in the outer core that are turbulent and chaotic and constantly shifting. No model includes all of this detail. No model could. The computational resources required would be prohibitive, and the data needed to constrain such a model do not exist. So scientists simplify, averaging over regions, smoothing out small-scale variations, focusing on the features that matter most for the questions they are trying to answer. This process of simplification is necessary, but it introduces uncertainty. Every assumption made in constructing a model is a potential source of error. If you assume the inner core is perfectly spherical, when it is actually slightly ellipsoidal, your predictions of how seismic waves travel through it will be slightly wrong. If you assume the outer core has uniform composition, when it actually has variations in the concentration of light elements, your models of convection and the geodynamo will be incomplete. If you assume the mantle above the core is homogeneous, when it actually has density variations that affect the gravitational coupling between the core and mantle, your estimates of how the inner core's rotation responds to external torques will be inaccurate. These are not hypothetical concerns. They are real limitations that researchers confront every time they attempt to interpret data or make predictions. The challenge is to identify which simplifications are acceptable and which introduce errors large enough to matter. The way forward is through iteration and refinement. You build a model based on the best available data and the most reasonable assumptions. You use that model to make predictions, and you compare those predictions to new observations. If the predictions match the observations, you gain confidence that the model is capturing something real about the core's behavior. If they do not match, you revise the model, adjusting parameters, relaxing assumptions, incorporating additional physics that you had previously neglected. Over time, through many cycles of prediction and comparison, the models improve. They become more accurate, more detailed, more capable of explaining a wider range of phenomena, but they never become perfect. There is always more detail than can be resolved, always more complexity than can be included, always some aspect of the core's behavior that remains mysterious because the data are insufficient or the physics is not fully understood. The scientists working in this field are aware of these limitations. They do not claim to have complete knowledge of the core, and they are careful to communicate the uncertainties in their findings. When a paper reports that the inner core's rotation may have changed, it includes caveats, error bars, discussions of alternative interpretations, and potential sources of bias. The media coverage of such findings is often less careful, simplifying the results into definitive statements that obscure the underlying uncertainty, but the scientific literature itself is more nuanced. The researchers know that they are building a picture from incomplete information, and they are transparent about what is known, what is inferred, and what remains uncertain. This honesty about uncertainty is not a weakness. It is a strength, a sign that the process is working as it should. Science does not claim to provide absolute truth. It provides the best available approximation of truth given the evidence at hand, and it remains open to revision when new evidence arrives. The core is a particularly challenging subject because the evidence is so indirect and the timescales are so long, but the principles are the same as in any other area of inquiry. You observe, you hypothesize, you test, you revise, you build models that explain the data, and you refine those models as the data improve. You accept that your understanding is provisional, that future generations may look back on your work and see errors and oversimplifications that were invisible at the time, but you do the best you can with the tools and knowledge available, and you contribute to a cumulative process that gradually converges on deeper and more accurate understanding. There is a kind of humility in this approach that is worth noting. The scientists who study the core are not claiming to possess secret knowledge or to have access to truths that others cannot verify. They are simply applying methods of observation and inference that anyone with sufficient training could replicate. The conclusions they reach are based on evidence that is, in principle, available to anyone who cares to examine it. The models they build are published, the data they use are often archived and accessible, the methods they employ are described in sufficient detail that others can reproduce their analysis or challenge their interpretations. This openness is essential to the process because it allows the community to self-correct, to identify errors, to build on successful ideas and discard those that do not hold up to scrutiny. The core, in this sense, is known collectively rather than individually. No single scientist has a complete picture of it. Each researcher focuses on some aspect: the seismology, the magnetism, the mineral physics, the geodynamo modeling, and contributes findings that are integrated with the work of others to form a composite understanding. That understanding is distributed across many papers, many research groups, many institutions, and it evolves as new data and new methods become available. The picture that emerges is not the product of any one person's insight, but the result of a collaborative effort that spans decades and involves hundreds of scientists from many countries and disciplines. This collective nature is one of the great strengths of modern science. It means that the knowledge is resilient, not dependent on the brilliance of any individual, and it means that errors are more likely to be caught and corrected because many eyes are examining the same evidence from different perspectives. And yet, despite all the collaboration, all the data, all the modeling, the core remains fundamentally mysterious. We know much more about it now than we did a century ago, and we will know more a century from now than we do today, but there is a limit to how much can be learned through indirect observation. The core will never be accessible in the way that the surface is accessible. You will never be able to visit it, to sample it, to conduct experiments on it in situ. You will always be working from a distance, interpreting signals that have traveled through the interior and emerged transformed, building models that approximate but never fully capture the reality they represent. This is not a temporary limitation that will be overcome with better technology. It is a fundamental constraint imposed by the physics of the planet, by the fact that the pressures and temperatures at the core are so extreme that no material known to science could survive them, that no drill could penetrate the thousands of miles of rock that lie above. In accepting this limitation, there is also a kind of liberation. The core does not need to be fully understood to be appreciated. Its existence, its role in shaping the planet, its slow evolution over geological time, all of this can be grasped even without perfect knowledge of every detail. The fact that it is changing, or may be changing, is significant not because it threatens anything or promises any immediate discovery, but because it reveals that even the deepest, most stable parts of the planet are not static, that everything is in motion, that change is the fundamental condition of the universe and occurs at every scale, from the rapid flickering of subatomic particles to the slow drift of continents to the patient cooling of planetary cores over billions of years. Somewhere beneath your feet, iron spins in darkness. It has been spinning for 1 billion years, perhaps longer, through epochs when nothing walked on land, when the atmosphere was still finding its composition, when the surface was learning what stability meant. It continues now in this moment, as it has through every moment of human history and prehistory, indifferent to observation, indifferent to consequence, following laws that were written into the fabric of the planet when it formed. The core does not announce itself. It does not send messages. It simply is, and it changes when the balance of forces requires that it change, and it will go on being and changing for billions of years more, long after any record of this inquiry has disappeared. The possibility that something has shifted within that spinning sphere, that the rotation has slowed or paused or reversed, is not a crisis. It is simply a detail in the ongoing evolution of the planet, a readjustment of momentum between layers, a response to forces that have themselves changed in ways we are only beginning to perceive. The Earth absorbs such changes without drama. The magnetic field persists, the heat continues to flow, the surface remains stable, life continues in its countless forms, unaware that deep within the world, something may have quietly altered its motion. We live on the thin boundary of a planet whose interior we will never touch. All that we know of the core, all that we can know, comes from echoes and shadows, from waves that have crossed the interior and returned bearing information encoded in their timing, from magnetic fields that reach the surface, but originate in currents flowing thousands of miles below. The picture we have built from these signals is remarkable in its detail, but it remains incomplete, forever provisional, subject to revision as new observations accumulate and new methods of interpretation emerge. This incompleteness is not a failure. It is the condition of knowledge about things that are remote and inaccessible, things that operate on timescales far longer than human perception, things that exist beyond the reach of direct experience. There is no urgency in this incompleteness. The core will continue to evolve whether we understand it or not. The processes unfolding there do not require human comprehension to proceed, do not benefit from being observed or studied or modeled. They follow the physics of heat and motion and pressure, indifferent to the fact that organisms on the surface have developed the capacity to wonder about them, to measure their effects, to construct theories about their behavior. The core is not waiting for us to solve its mysteries. It simply continues, patient and constant, a presence at the center of everything. And in that patience there is something calming. The world is not fragile in the way we sometimes imagine. It does not depend on every detail remaining exactly as it is. It can accommodate change, absorb it, integrate it into new configurations that preserve the essential conditions for stability. The core can shift its rotation, the magnetic field can wander and reverse, the mantle can reorganize its convection, and the planet endures, finding new equilibria that allow it to continue functioning as a coherent, dynamic system. Change is not catastrophe. It is simply the way complex systems evolve over time, moving from one state to another according to principles that are fundamental and indifferent. We observe these processes from a distance, both spatial and temporal, trying to understand what is happening in places we cannot reach, on timescales that exceed our lifespans. The effort is worthwhile not because it provides control or protection, but because it expands the boundaries of what is knowable, because it connects us, however tenuously, to the deep workings of the world we inhabit, because it reminds us that the planet is larger and older and more complex than the thin shell of surface experience suggests. The core is there, spinning in darkness, releasing heat, generating fields, changing slowly according to its own internal logic. It has always been there, and it will remain long after everything on the surface has transformed beyond recognition. That constancy, that patient continuation, is perhaps the deepest lesson the core offers, though it offers no lessons intentionally. It simply exists, and in existing it provides a foundation for everything above it, a stability that operates at scales so vast that it becomes invisible, taken for granted, noticed only when scientists with seismometers and magnetometers and centuries of accumulated observation detect the subtle signs that something somewhere deep below may be changing in ways that unfold too slowly to see, but that are real nonetheless. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.